Hello my friends, and welcome back again to another video for Physics Paper 2 for AQA. This session we're going to be looking at magnetism. It is a wonderful topic, however most of it is glossed over, and of course we don't get into much detail on it because magnetism is quite difficult to get our heads around, something we still don't really fully understand. Anyway, so we're going to look at what permanent magnets are, we're going to consider electromagnets, we'll look at something called Fleming's left-hand rule, we'll look at the motor effect, the generator effect, how that then explains the use of electromagnets in speakers and microphones, and finally in transformers. Okay, so when we're looking at magnets, we are talking about an interaction between what we call a north pole and a south pole. So it's always a north versus a south, so any magnet will have a north end and a south end. And when we're looking at the magnetic field, we also always draw our magnetic field going in the direction of north to the south. What this arrow actually tells us is the force direction that would affect a north pole if it came into that vicinity. So if you had a north pole here, it would get forced away that way. If you had a north pole here, this part of the magnetic field diagram, it would get forced towards the south. If you had a north pole at this end, it would get forced away from the other north pole. So we're talking about this idea of attraction and repulsion. On that kind of note of attraction and repulsion, so an attraction is always between opposite or unlikes in terms of poles, so a north to a south or a south to a north is going to cause an attraction, whereas repulsion comes from two like poles facing each other, so a north and a north, or a south and a south. The other thing that we're going to look at here is the idea of the three types of metal that are magnetic or can be magnetized, which are FeNiCo. Fe is iron, Ni is nickel, and Co is cobalt. That means that any of these can be put into an alloy as well, so they can be put in a mixture of metals and become magnetized and magnetize that metal alloy. But it is these three that can be magnetized. The other two keywords we're going to look at here are permanent and induced. Permanent refers to permanent magnet, so a magnet that has been magnetized, which can be done by stroking a magnet along it, for example. That is going to be magnetized whether it is in a magnetic field of another magnet or on its own. It will permanently stay magnetized. It produces its own magnetic field. However, an induced magnet is only a magnet when inside the magnetic field of another magnet it becomes a temporary magnet. And if we take it out of that magnetic field, it will lose its magnetism, its magnetic property, and it will lose most of it or all of it pretty quickly. When we look at magnets, we can represent their magnetic property and how they're going to behave based on their magnetic field. And so what we draw is a diagram like at the bottom here. So this is a magnetic field around a bar magnet, and you can see that it's got varying field lines, and the strength is determined by the number of field lines present. So the strongest magnetic strength of this, strongest place in the magnetic field for this magnet will be at either pole, where there are the most magnetic field lines in the closest proximity to each other. The direction of the field lines shows the direction of a force that would act on another north pole at that point, as we said earlier. And the skill that we have to be able to demonstrate for magnetic fields is how to plot a magnetic field of a magnet using a compass. And you might have used these in class. These little penny compasses are very small. The compass point can turn around. And what you would do is mark it on a bit of paper next to your bar magnet. You'd place it on that point. You'd mark either end of that magnet. You'd take the magnet away and you'd join the two up with a ruler. And you keep doing that at different points across this page. You end up with compass points, which look a bit like this. Again, marking each point of where the compass points are on your page. And you end up getting a nice big looping field line. You'd keep doing that at different points and hopefully form a few different field lines, and you could see how it's interacting, and you get a very nice collection of field lines and the direction that the field is acting in. Now we've looked at permanent magnets and how magnetic materials can be induced. We're going to look at how we can create magnets by using electricity. And this is based on the property that when you have a conducting material like wire, copper wire, anything that has electricity that runs through it, the current running through it will produce a magnetic field. The electrons running through these wires produce a magnetic field. And that magnetic field has a certain direction and properties based on how much current is running through it. So the strength of that magnetic field is going to depend on how many electrons are passing through it every second, which is the current. And the strength is also going to depend on the distance from the wire. And the reason for this is the same as what we looked at in the previous slide, to do with the field lines. That close to that wire, field lines are closer together, and the further you get out from the wire, the further out they become, further apart they become. So the further away they are from each other, the less strength and magnetic field there is. So here in the middle you've got very close proximity, further out they're further apart, so you've got less magnetic field strength. It's called flux. And again, to find a magnetic field around the wire, what you could do is, like in this diagram here, let me just clear all of this, you could put a bit of wire going up through a piece of paper, and on that piece of paper you have it nice and flat. You could put down some compasses again, just like we did before, and you should find, if you arrange them in a circle around that wire, that they're all facing in a circular shape, circular pattern. And that's because it's a rule of how the electricity causes a magnetic field. You can see here we've got the flow of current. Bear in mind that flow of current here is the conventional current, which is positive to negative. So we're going up through this wire. And the corkscrew rule applies to determine the direction of the magnetic field. And that's using the right hand corkscrew rule. So when you're sat in your physics exam, you can, for paper 2, you can probably be looking around the room when you get to this question, and you'll see lots of people putting their right thumb up and making a corkscrew shape, as I am in this picture. And it shows that as the current is coming up, the direction of the magnetic field is in that direction, which is anti-clockwise, which makes my diagram absolutely incorrect. So a solenoid is just an extension of that wire, showing that it has an electric field when you've got current running through it. And a solenoid is just a coil of wires, and it behaves in just the same way. So if you have your electric current running in a positive to a negative direction, which is the conventional way of looking at it, it's not the actual way that it flows, but it works for magnets at least. In this case, we apply our corkscrew idea, or a right-hand corkscrew rule, and we can find that if you put your thumb up there, that the direction of the magnetic field is moving in a circular pattern like this. And if you did this for every single wire that's going up, at least, you end up with this circular pattern. So one here as well, and here and onwards. And where we've got it running down in the far side of this coil, it would actually be rotating around the other way. But what that basically means is around every single one of these coils, you have in the inside of the coil, the magnetic field is moving this way. On the outside of the magnetic coil, it's running back round again on itself, like that. So if we look at a cross-section, looking down from on top of this solenoid, or electromagnet if you like, we actually see it's exactly the same structure as a bar magnet. The field is exactly the same as a bar magnet. We've effectively created a bar magnet by coiling these wires in this particular way. And it makes a lovely, strong and uniform magnetic field, just like a bar magnet does. And again, to increase the strength of this, just the same as before, we can increase the current. We can increase, have the strength that's obviously closer to the wires too, as we saw earlier. But if we wanted to increase the strength of the solenoid, what we can do is increase the number of turns. Increase the number of turns. And how close together they are as well. So nice, densely coiled turns. It's not the number of coils that we're increasing. So we cannot refer to the number of coils, it must be the number of turns, otherwise you won't get the marks. The other way that you could increase the strength of a solenoid is to include an iron core. It doesn't have to be iron, but iron is very easily magnetised, and to do that you would just get a nice chunk of iron, place it inside the coil, and what that iron, it doesn't need to be magnetized, the iron, but once it's inside the magnetic field of the current carrying wire, it will become an induced magnet, and so it will become magnetized, and that will really increase the strength of this solenoid. It will actually make it into a proper electromagnet. So on to our first part, which is highlighted here, and this is looking at something called the motor effect. Now, motors are all about moving, so this is a movement effect that we get from using electromagnets and from using wires and current, basically, encourages a force. So these are the mark points that we get if we're trying to explain what a motor effect is. So when a current-carrying conductor is placed in a magnetic field, the magnetic fields of both the magnet and the conductor interact. And that is a really, really critical word that you have to use, they're interacting. This interaction causes the magnet and the conductor to exert a force on each other. And once again, force, really important. Exerting is just a nice word you could use. You could say making a force or having a force on each other, but exertion is the best way to describe it. And so if you have, as an example here in the bottom right, you could have a positive and a negative running along this bit of metal, which then has a bit of metal here which is running across them, which can roll, which is free to move, and then it's going to run back the electricity. So in a positive to negative direction, we're going to have the current flowing this way, and along this bit of metal which can roll, it's going to be moving this way. We also should know the magnetic field that you're going to have existing. So let's say that this is north and south, and for the other side we've got a south and a north, and magnetic field always goes in a north to south direction. So magnetic field is going this way. Now, to find out the direction of the force that's enacted upon this metal rod that can roll, we have to apply something called Fleming's left-hand rule, which you need to know the name of, and we need to know which fingers or thumb represent which part. And so the way to remember this is for thumb, the M stands for motion, so that's for force. So the thumb is for force, the first finger is for field, and the second finger is for current. And they are on a kind of X, Y, and Z plane, if you like. They're 90 degrees to each other. So again, you might be sat in the exam, glance around a room, and you see a whole bunch of people with making weird shapes with their hands. That's exactly what they're going to be doing. So if you align that with our diagram that we have here, you've got the second finger pointing out of the screen towards you. You've got the field is running down, and as a result, you should be able to see that your thumb is pointing to the right, which tells us this metal rod is going to start rolling to the right. If we were to flip the direction of the current, so instead we had negative on the top, positive on the bottom. We just remove these arrows and we draw this all around the other way. So negative and positive. We've got the current is running now from the positive to a negative direction that way. The magnetic field is working exactly the same. So what we've in effect done is made the force go in the exact opposite direction. To explain this a little bit more, we have an equation that we're given. This one is on the equation sheet, as I say, we don't need to learn it, which is F equals B times by L times by L. Now, in this, the force of the movement, which is in newtons, is equal to B, which is actually the magnetic flux density, is measured in Tesla, like the car. Magnetic flux density is just the field strength of the magnets, so it's how much magnetic field strength there is actually in the region where the force is going to be enacting. I is the amount of current, which is measured in amps, and L is the length of the wire that's in the magnetic field. So to increase the amount of force, we could increase either the strength of the magnets, the current that's running through the wire, or the length of the wire that's in the magnetic field. And you'll be given numbers just to put into that equation. Okay, so we're going to look at some uses of the motor effect, and the first is in, quite logically, an electric motor. And electric motors work on the principle that we just considered, so the idea that magnetic fields of both the magnet and the conductor, the wire, they interact. And that interaction causes the magnet and the conductor to exert a force on each other. So if we look at this example here of an electric motor, you've got one magnet on top, or to the side, and another magnet on the other side. So you have a magnetic field running north to south across this space. You've then got a loop of wire. Let's say you've got positive on this side, and it runs this way around the loop, along here, back down to the other side, along this way, back to the negative terminal. Now, as we know, with Fleming's left-hand rule, we have the motion in the thumb, we have the field on the first finger, we have the current on the second finger. With that, we can find out the direction of the force that these two bits of a coil are going to move. Now, bear in mind that this is usually on some sort of an axle, so it could be attached to a cog that then turns an axle which turns wheels. It could be in your phone as the vibration generator. It could be anything. But the working behind it is quite simple. So we've got the current moving through this loop. As the current is moving here, it's moving in a direction countering the magnetic field. And so the magnetic field of the electrons moving through that wire and the magnetic field of the actual magnets themselves are going to interact and cause a force. And we can again find out the direction of the force of this bit of wire. So if you get out your hand and you're arranging it in the Fleming's left-hand rule way, and you arrange your second finger with the direction of the current, which is this one, it's going to the right. If you then arrange your first finger to be going down the screen, it's quite a difficult way to arrange it, isn't it? And then you can find out that your field is absolutely, I'm here squirming trying to get it arranged, is going to go down into the screen, if you like, or into the page, whatever you're looking at. On the other side of the coil here, the current is moving the opposite direction. So if the current is moving the opposite direction, the movement of the force is going to be opposite too. So you could work this out. You can arrange your current to be moving to the left. You've got your field moving down the screen still, and as a result, you can see that the force is going to come up. So if this coil is arranged on an axle, it can rotate, and so the top side is going to be rotating down, and the bottom side is going to be rotating up. So if you imagine then, if we look at it horizontally from the side, this is our coil of wire. You've got the left side is going to go down, and this side is going to go up. So it's going to rotate around to kind of this position. And eventually it's going to rotate around to this position until it's vertical. Now if you've got a direct current running through these wires, if you've got a direct current running through all of these, that's going to end up making it just stay in a vertical position, because that's going to be at balance. The bottom's no longer going to want to move any further around, the top's not going to want to move any further around, it's not going to do this or anything, and it would stay put, and that would make a pretty useless motor. So what we have to have attached at this end of the coil is something called a split ring commutator, which is a very cool word, a very cool phrase. Whoever named that top, my hat is doffed to you. Now, what this does is it basically is a circular structure. So if we actually draw it around the horizontal view that we've already just added here, it kind of looks a bit like this. So we've got our electrode for a positive and a negative are separated by a physical gap. And the wires here have brushes which kind of attach to this split ring. So you'd have one brush attached to the positive side and one brush attached to the negative side. As it rotates around, they're still attached, and this is rotating up. It's still going to be attached to the negative until it reaches this point absolutely vertical, where neither of the brushes from this coil, from the spinning coil part, are attached to the commutator. And the momentum of it spinning up or down, spinning around, will cause it to actually carry over and touch the new terminal. And what this does as a result, if you see the text on the left here, this is from a mark scheme, it swaps contacts every half turn. And by swapping the contact every half turn, it's reversing the current every half turn. And what that means is we've actually caused this this part of this coil, it was negative, it's now become positive, and as a result it was being forced up, and now because it's positive it's going to get forced down. And this one at the bottom, it was positive here, and so it's being forced down, and then it became negative, and now it's being forced up. So it's going to cause a constant spinning around, which is magic. Keeps the rate of rotating in the same direction. And honestly, it is a bit of magic, isn't it? It's quite impressive. If we're looking at alternating current, though, alternating current will have each bit of wire in this coil permanently attached to the same kind of terminal, so it would be always positive or always negative. If you remember alternating current, you have your picture, your diagram. Alternating current looks a bit like this, so you have a positive direction and a negative direction, constantly flipping. In fact, in the UK it's 50 Hertz, isn't it? You would have learnt that for paper 1. So basically what this means is you can actually cause the motor to start spinning, and it should rotate at a frequency of 50 Hertz itself, because the current is always changing direction, and if that's in sync with how it's rotating and spinning around, the direction of the force will also rotate or flip 50 times every second, and it kind of does it itself. But the one that AQA will want you to look at more is the direct current motor and how that works, absolutely explaining the need for a split ring commutator. So with the motor effect, we had a current and we had a magnetic field. And these two moving relative to each other or existing with each other caused a force, which was pretty magic. What if we don't have the current, but we have the force and we have a magnet, and we're moving a wire through a magnetic field? What's going to happen? Because previously we had the current moving through the magnetic field, which created a force. Can we create a current if we move a wire with force through a magnetic field? Well, absolutely we can, and we do. And this is a generator effect. And this is a physics and higher tier skill only. So generator effect creates something called an induced potential. So this is the kind of explanation, the rule again taken from Mark schemes. This is exactly how AQA want to see it written. If a conductor moves relative to a magnetic field, or there is a change in the magnetic field, then a potential difference is becoming induced. So we're creating a potential difference. Now, if it is part of a complete circuit, as in it's a full loop of a circuit, electrons can move all the way around this circuit, then we're going to get a current being induced too. So let's just review that a second. So if the wire is moving through a magnetic field, we're going to get potential difference and a current. Or if we have a wire sat in a magnetic field and that magnetic field is changing, then we're going to get the potential difference and a current being produced. So to highlight that point, if we have here a magnet which has a north end and there's a second magnet which has a south end, so we have a magnetic field that's running this way, and we take this wire and we move it with force up. If you get out your left hand again, Fleming's left hand rule, you've got your force, which is the thumb pointing up, you've got your field, which is your first finger pointing this way towards you. Your current is going to be going this way. If you were to force it down instead, you're reversing completely the direction of current, it would go that way. If you reverse the magnetic field, again, you're going to cause the direction of the current to be changed. So it's quite a nice question there, is actually saying, well, if you've got this setup and the current is moving this way to the left, what could you do to the setup to change the direction of the current? So you could flip the magnetic field, or you could flip the direction of the movement, the force, and that applies to the motor effect too. So to get a different direction of force, you could change the direction of current, or you could change the direction of the magnetic field. But just to highlight again the kind of mark points they might want to see, so this induced current generates a magnetic field too, and this is opposing the original change. So the current, the movement of it is going to try and change the force from occurring. So if you think about the motor effect, if we're moving the conductor up, the current is going to be moving away from the direction it's trying to force it. So it's not going to be a positive feedback system where it then forces itself further, it's going to be a negative feedback system. So it's going to want to basically not move anymore. So if we look at then how we can use the generator effect, we can look at actual generators, again a physics and a higher tier skill only. So we can look at generators as DC, so direct current, or AC as being alternating current. In DC, we're calling these types of generators called a dynamo, and exactly the same as a motor, the exact same setup. We've got a magnet, we've got a coil, we've got a second magnet providing a magnetic field. We have the option of providing a movement of current here. But rather than providing current, we're instead providing force. So we're going to spin this coil in the magnetic field, or we're going to spin the magnets around the coil. And what we end up having is, again, the magnetic field inducing a potential difference and a coil current in that coil. But we need to have a split ring commutator because, again, this is going to maintain the same direction of current by swapping the connection, the brushes with contacts every half turn. And if you want to review that, go back and look at the motor effect. We'll explain how that works a little bit more. But without those, you'd end up getting AC generation, which is called an alternator, and the rotation of the coil naturally leads to the current reversing every half turn. So you end up getting a graph that looks like the typical AC generator, AC potential difference graph, with it reversing every half spin of this coil, aligning itself with whatever frequency of the axle turning is. For the direct current one, however, because of the flipping every half turn, we end up with a system, a graph that would look like this, which isn't the perfect direct current graph that you might have seen from the electricity topic, but we call it direct current because they are all still positive. Still a positive outcome, whereas this has a positive and a negative parts to it in the cycle. Another application of the motor effect and the generator effect is in loudspeakers and microphones. Now, these are two uses of electromagnets that we need to be aware of, but they could quiz you on a few others too, where you get given a diagram of, or a circuit diagram of how it might work, for example, an electric bell, or a door lock or a switch or something like that, and you have to try and work out how it works. But for a loudspeaker and a microphone, it's just a perfect example of how a motor effect and a generator effect will work. So in a loudspeaker, the motor effect will convert variations in the current which are being delivered to the movement of a magnet which is attached to the membrane in the speaker. So the current is arriving, and you might have seen this kind of picture of where you've got a kind of zero axis, and then sound waves kind of look like this. You see them on SoundCloud and that sort of thing. That's the variation in current that's being delivered through the electricity to the speaker. And what each of these little fluctuations will do will cause that force on the speaker, on the membrane, this red part here, will cause a force on that because you have a coil of wires which have the current running through it, which is sat inside the magnetic field. So it will either cause the speaker to be forced out, or you're caused to force in, and that movement in and out from of these magnets will cause then vibrations in air and send out waves of air particles. And these waves will have a matching frequency and amplitude to what was delivered in the current to the actual loudspeaker itself. And for a microphone works in the opposite. So if we go back and remove all of these, a microphone will have sound waves coming in. These sound waves will carry a certain frequency and a certain amount of amplitude, so that's the loudness, which will cause this coil of wire and the membrane to move in and then spring back out again at a certain frequency and a certain amplitude. And as it moves through this magnetic field, which is running here, as it moves through that, it's going to generate current in the coil of wire, and that coil of wire's current will then be detected, probably be amplified and then recorded, and that will record the sound wave as what we saw earlier, and that will be the electrical recording of what the sound was. Isn't that magic? That can then again go to be played at a speaker, work exactly as we just saw. Transformers are another application that we need to be aware of for how magnets work, and they follow the rule that we saw earlier, that if there is a change in the magnetic field, then a potential difference is induced across our conducting component, our wire. So we have working here, we have a wire with an incoming current which is going to be alternating. It's an alternating current. So when it's working, it's going to set up a magnetic field which is going to turn this iron core and make it have a north pole and a south pole, or a south pole and a north pole, and these are going to alternate and switch between each other as the current is alternating its direction and coming in. And that's also going to cause a magnetic field to be formed at this end of the iron as well, which is also going to be alternating. So if the magnetic field is alternating here, it's going to cause an alternating current to be formed in the wire too. So we're inducing an alternating current, we're inducing an alternating potential difference. Now there's an important rule that we're going to apply here, which is that the ratio of potential difference across the first and the primary and secondary coils is equal to the ratio of the number of turns on the primary and secondary coils. So if we put this into an equation format, which is one that we're going to get given on your equation sheet, that is that the VP, so this is the primary side and this is the secondary side, VP divided by VS is equal to NP over NS. So this is a ratio of voltage, potential difference, and this is a ratio of the number of turns. That ratio is equal to one another. So if on the left hand side we have a voltage of 5 and on the right hand side we have a voltage of 10 being created, if we have 3 coils on the left, there's going to be 6 on the right. So by increasing the number of coils, we're increasing the number of volts we get. And with that, we can apply 2 terms that we learned in the first paper. We have step-up transformers and step-down transformers. A step-up transformer is when we're increasing the voltage, so where the voltage on the secondary coil is greater than the voltage on the first coil. And on the step-down, we find that the voltage on the secondary coil is less than that on the voltage on the primary coil. So the 2 equations we're given. First is VP over VS equals NP over NS. So the ratio of voltage is the same as the ratio of the number of turns. And the second one is going to be relating to power. So this is based on the idea, which is not true, that if the efficiency of this transformer is 100%, the power output is going to be equal to the power input. So let's write that in a different way. So PS, so the power for the secondary is going to be exactly the same as the power for the primary coil. Now, in electricity as a topic, you learnt a definition of power. You learnt it as power equals energy divided by time, but you also learnt it as power equals current times by volts by the potential difference. And so if we expand this power rule of being equal on both sides a bit more, we can say that the current for the secondary times by the voltage for the secondary is the same as the current for the primary multiplied by the voltage on the primary coil. So if we have in a setup of on our transformer a number of coils that maybe is n equals 3, and on the other side we have n equals 9, so we have 9 of the coils, 1, 2, 3, 4, 5, 6, 7, 8, 9, you get the idea. If we have then, let's say 10 volts coming in on the left hand side, and we can work out using our first equation that there would be 30 volts being produced on the right hand side. But if we then got given on the left we had 1 amp, we could find out how many amps we had being used on the right hand side. So using the same equation as we just wrote down, we could expand this. So again, remember that you get a mark for writing the correct equation, you get a mark for then substituting correctly. So we don't know the current for the secondary, but we do know the voltage, which is 30. 30 is equal to 1 times by 10. So we can then kind of solve that a bit more, so you get marked for substituting. So that'd be 10 is equal to IS times by 30. We rearrange this, moving the times by 30 over to the other side, so we get 10 divided by 30, which is equal to 0.333. Stick with 3 significant figures unless it tells you otherwise, and that's IS. So we can find out that nice and easily, amps. And in the national grid, again, back in paper 1, they might ask you about this. They talked about why we use lots of step-up transformers after using a power station. So step-ups are used to increase the voltage and reduce the current, because if you reduce the current, we are reducing the energy loss through resistance, so reducing the electron movement. There's less collisions of electrons with the ions, metal ions that are left in the wire, and as a result there's less heat being generated, and so less loss of heat. and of course we'll then step it back down to come into houses and workplaces and things like that to make it a lot safer for use. Good. Well, that's our overview of magnetism done. Well done, everybody. Thank you for watching. Please do click like and subscribe.